Compact tri-bandpass filter. In result, now we will discuss s11 and s21 graphs. In previous tutorial I have already discussed individually. Now I will import s21 graph and s11 graph. Then I will tell you how the practical meanings of insertion losses and transmission zero, and also I will tell you why we take fractional bandwidth at -3 dB. The reason of taking at -3 dB. Now first of all I am going to do some changing in the graph properties. If you don't know, you can search in my HFSS tutorial series. Double click on HFSS. Now I am going to this is s21 plot. Now I am going to export this graph and then I will import this in on a s11 graph. Select.txt file. This is s11 plot. Now I am going to import this s21 graph and s11 graph. Now here you can see that this is s11 plot, then add this is s21 plot. Now I am going to mark transmission zeros. These are the transmission zeros. Now I am going to mark the insertion losses. Now I am going to mark at -3 dB for fractional bandwidth. Since you know that transmission zeros are always created at the start of the band and at the end of the band. This is first transmission zero. Here value you can see that this is created at the end of the first passband. And similarly, this is second transmission zero, which is created at the start of the second passband, and this is third transmission zero, which is created at the end of the second passband. Here, this is the fourth transmission zero, which is created at the start of the third passband. This is the fifth transmission zero, which is created at end of the third passband. Here this line must be goes from there. Because of mismatching, here is problem. The structure of this graph is due to mismatching. These are the transmission zeros. Now look at, there must be at the start of the first passband needed and a transmission zero, but the transmission zero is not created. For tri-band bandpass filter, we always needed a 6 transmission zeros. If greater than 6, it's okay, but less than 6 makes mismatching and other problems. Now look at the transmission insertion losses. This is insertion loss. What is the definition of insertion loss? Insertion losses take place in the result of insertion of load in a transmission line. Since it is s21 plot and this is s1 plot, this is s21 plot. Since it is s21 plot, it means the power is entering from port 1 and power out from port 2. In this result, the insertion losses take place. Any change or signal come out in passband. Insertion losses must be found during the passband, s11 passband. This is the passband of s11. These insertion losses calculated here. That is why I have selected the maximum point of this graph from here to here. It shows the losses in the result of insertion of load in a passband. Similarly, this is M6. You can see that. Similarly, M7 shows the insertion losses of second passband, and M8 shows the insertion losses of third passband. M8 shows the insertion losses of third passband. These are the practical explanation of insertion losses. Here you can see that at the start of the passband they are measured. Now I am going to tell you why we take fractional bandwidth at -3 dB. Here you can see that these two graphs touches each other at -3 dB. This is M14. Here you can see that M14 y-axis at almost at -3 dB. That is why we measure at -3 dB because the fractional bandwidth of these two always find where these two graphs are touches with each other. Similarly, M10 at -3 dB. Likewise, M11 at -3 dB. M12 at -3 dB. Similarly, M13 at -15 dB. Because of mismatching, here is a very big mismatching occur. That is why our graph is not made properly. But actually, we take fractional bandwidth at -3 dB. Similarly, we find insertion losses this way, transmission zero that way, In coming tutorial, I will discuss how to create a transmission 0 at our desired position. And similarly, I will make a tutorial how to shift these passband. If I want to shift from this position, it is working on this much position, almost 2.2 at 2.2 frequency. If I want to shift this passband to 1.9 gigahertz, I can shift it without affecting the position of other two passband. Similarly, third passband and similarly first passband, I can shift it. We will discuss in coming tutorials. Similarly, you always keep in mind the passband values must be greater than from -10 dB, because we measure the bandwidth of a filter or useful frequency peak if it is down from -10 dB from these points. We always find the bandwidth of a passband at -10 dB. This is the lower cutoff frequency and this is higher cutoff frequency. This is the lower cutoff frequency, this is higher cutoff frequency. This is the lower cutoff frequency and this is the higher cutoff frequency. This is the lower cutoff frequency of first passband and higher cutoff frequency of first passband. Lower cutoff frequency of second passband and higher cutoff frequency of second passband. Lower cutoff frequency of third passband and higher cutoff frequency of third passband. You can see that the transmission zero is always created at the start and end of the band to improve the selectivity and best matching result. And also these transmission zeros are necessary to isolate the two passband from each other. First passband and second passband can be isolated in this way. It is necessary the first passband must be isolated from second passband and second passband must be isolated from first and third. So that is why the transmission zeros are also used as an isolation of the passbands from each other. By zooming it, you can check it. If you are not getting these instruction point, here you can see that this is not at exact intersection point. You can zoom it and then you add point here. Similarly, this is not at exact touching point where the two graphs intersect each other. You can zoom it and then add. Let us suppose I am doing that. Now I am going to zoom it and mark a point where the intersection of these two comes out. The mark is only possible on grid lines. You can see that without grid line it is very difficult to mark. So move it such a way that you get now you delete this. Here you can see that now it is marked on a correct position. Similarly, you can mark a for others. You can add nodes. Similarly, you can label them. You can mark as insertion losses point or bandwidth or fractional bandwidth and transmission zeros.